Hi, we're going to learn about independent and dependent events, but first we'll do a warm-up that has you looking back at conditional probability scenarios. In each scenario, you are drawing one card from a deck of cards. Number 1. Given that Winston has added 2 jokers into a standard deck of 52 cards, what is the probability of drawing a club? There are originally 52 cards in the deck. With 2 jokers added in, there are now 54 cards. And out of those 52 cards, there are 13 clubs. The probability then is 13 out of 54. Number 2. Given that Philip has removed all of the clubs from a standard deck of 52 cards, what is the probability of drawing a face card? So we don't have the jokers in. It's the standard deck of 52 cards. There are now no longer any clubs, so we have to figure out how many cards are left if we take out 13 clubs. That would be 39. Out of those 39 cards, what's the probability of drawing a face card? The face card is Jack, Queen, or King, and there are 4 of each of those. 4 of each of 3 faces is 12 total. 12 face cards out of the 39. So the probability of drawing a face card is 12 out of 39. Those numbers are divisible by 3. So you could reduce the probability and say that it is 4/13. Number 3. Given that Elizabeth has removed all of the aces from a standard deck of 52 cards, what is the probability of drawing a heart? Well, there were 52 cards. We pulled out all the aces. That's 4. So 52 minus 4 is 48. Now we only have 48 cards to draw from. What is the probability of drawing a heart? 1/4 of the cards are hearts. So that's 13 total. That makes the probability of drawing a heart 13 out of 48. Number 4. Given that Melanie has rolled a 7 when rolling 2 6-sided dice, what is the probability of drawing the 3 of clubs? Alright, now if this seems a little confusing because you're wondering, how are these two events related, rolling 2 6-sided dice and drawing the 3 of clubs? Well, they aren't related. So the probability of drawing the 3 of clubs is still the same as it would have been if there hadn't been these dice that Melanie is rolling. These events are called independent, and you're going to learn more about that in this lesson. What it means for events to be independent versus dependent. So what's the probability of drawing the 3 of clubs? There are 52 cards in all. There is only one card that is a 3 and a club. So the probability is 1/52. Number 5. Given that Gary just leveled up his Magikarp to 100, what is the probability of drawing a red card? Well, you don't need to know what it means to level up his Magikarp to 100. You just need to realize that that doesn't have anything to do with drawing a red card. So these two events are independent. One does not affect the other one. So the probability of drawing a red card is figuring out how many red cards there are total out of 52. Half of the cards are red, half of the cards are black. So 26 out of 52, or 1/2. The probability is 1/2 because half of the cards are red. Rewrite the question below to remove any unnecessary information. Briefly explain why you removed what you did. Miranda rolled a 9 with 2 6-sided dice on her previous turn in a game of Monopoly. What is the probability that John does not roll a 9 on his turn? John not rolling a 9 is a separate event from what Miranda rolled. So it doesn't really matter that Miranda rolled a 9 on her turn because her turn is independent of John's turn. These are independent events. What is the probability that John does not roll a 9 on his turn? We can find that out whether we know what Miranda rolled or not. I'm not going to find the probability. I just want to point out that these events are independent, so we can cross out the part that I crossed out. We say that events are independent when the occurrence of one event has no impact on the occurrence of another. Conversely, events are dependent when the occurrence of one event affects the occurrence of another. Let's see if you can remember some of these probability formulas that we've talked about. It's okay if you can't. I'll write them down for you. And sometimes there are ways to do these without knowing these formulas as well. Recall, if 2 events A and B are dependent, P of A vertical line B equals, well, that is the probability of A given B. So the denominator is the probability of B happening because we are assuming that B has happened. And then the probability of A, given that B has happened, would be the probability that both A and B have happened. We can write that as the probability of the intersection of A and B. That's the probability of A and B both happening, divided by the probability of B. What is the probability of A intersection B, the intersection of A and B? If the two events are dependent, that means one affects the other, then the probability of both events happening is the probability of A multiplied by the probability of B, given that A has already happened. Second section, but if two events A and B are independent, the probabilities are easier to calculate. The probability of A given B is just the probability of A happening, because it doesn't matter if B has happened, because B does not affect A. So the probability of A given B, if they are independent events, is just the probability of A. Probability of A intersection B, the probability of the intersection of two events, because they do not affect each other, it is simply the probability of A multiplied by the probability of B. Now, whenever we have formulas put down, it can be really easy to feel like you don't understand why those formulas work, what they mean. So I would encourage you to think about how to solve probability scenarios when possible without thinking about these formulas. Now let's look at more scenarios together. Consider the following. A jar contains 15 red marbles and 17 yellow marbles. Suppose you draw 2 marbles, hoping to draw a yellow marble first and a red marble second. Part A. How do the marbles need to be drawn so that each drawing is independent of each other? Find the probability of drawing yellow then red under these circumstances. In order for these events to be independent, you need to draw a marble and then put it back, and then shake the bag up again, make sure everything's mixed up, and then draw a marble again. When you put the marble back, you're starting over in a sense. So if these events are independent of each other, the probability of drawing a yellow first, there are 17 yellow marbles, and you want to draw one of them. So 17 of the marbles in the bag are yellow, and in total there are 15 plus 17 marbles to draw from. So 17 out of 32 is the probability of drawing a yellow. Then you put the marble back. The second marble that you draw, you're trying to draw red. There are still 32 marbles in the bag because you have put the first one back, and 15 of them are red. So the probability of drawing yellow then red is 17 over 32 times 15 over 32. Now, I'm not going to simplify that because we don't need to. Part B. How do the marbles need to be drawn so that the second drawing is dependent on the first? Find the probability of drawing yellow then red under these circumstances. So we kind of talked about this in the part A. If we were to draw a yellow first, there are 17 yellows out of 32 total marbles. But if I want the second drawing to be dependent on the first, then I would not put the marble back. Now there are only 31 marbles to draw from, and I want to draw a red, so I have 15 to choose from. As you can see, the part A and part B probabilities are similar, but there are differences in them, because the second scenario is dependent events. A spinner is equally divided into 4 green sections, 3 red sections, 2 blue sections, and 1 yellow section. What is the probability that the spinner stops on green, then yellow, then blue? These are independent events. Each time you're spinning it again, it doesn't really matter what you landed on before that. So let's look at these with colors. The probability that you land on green, there are 4 green sections out of 10 sections in all. And then the probability of landing on yellow, there's only 1 yellow section out of the 10. And then lastly, you want to land on blue. There are 2 blue sections out of 10. So the probability of these events happening in that order is the probability of each one separately multiplied together. And that would be 8 over 1,000. And you can reduce that fraction as 1 over 125, or you could write it in its decimal form, which is 0.008 or 0.8%. So less than 1% chance that happens. Number 2, a rental dealership has 4 white cars and 2 silver cars available. 3 customers are in line waiting to be assigned a car for their road trips to Hawaii, Puerto Rico, and Japan. A. What is the probability that all 3 will be given a white car? This is dependent probability, because once a car is taken, it is taken. It's not available anymore. So the next person up has less cars to choose from. So let's look at this scenario one piece at a time. The first person has 4 white cars to choose from out of 6 cars in total. So they have a probability of 4 out of 6 that they will be given a white car. The next person has only 5 cars to choose from, and if one of those cars has been assigned, there are only 3 white cars left that can be assigned. And that person is getting a white car, so they have a 3 out of 5 probability. Now there are only 4 cars remaining to choose from, and the next person is given a white car, so there are 2 white cars to choose from. Now we can multiply these probabilities together. I will cancel some things out before I do. That would be 3/15 or 1/5. Now you can also do this scenario using combinations. There are 4 white cars that we have to choose from, and we are trying to choose 3. It doesn't matter what order they are picked, but it's 4 choose 3. The total number of cars to choose from is 6, and we are trying to count how many possible ways we can select 3 of those cars. That's the denominator. 4C3 divided by 6C3. If you calculated it out by hand or using a calculator, you would also find that that is 1/5. Part B. What is the probability that 2 will be given a white car and 1 will be given a silver car? Using combinations, there are still 6 cars that we are selecting from, and we want to choose 3 of them. So the denominator of our probability fraction will be 6C3. To look at the numerator, let me consider these people standing in line in the first position, second position, and third position. So one way these cars could be given out is that a white car is given first, a white car is given next, and then a silver car is given third. We could do a different arrangement. First it could be silver, then white, then white. And there's another order. We could have white, and then silver, and then white. And those are the only 3 ways that we can set these up. Now let's look at how many ways we can select the white, white, and then silver. There are 4 white cars to choose from, and then there are 3 white cars to choose from, and then 2 silver cars to choose from. But we need to divide by how many ways we can arrange the 2 white cars because the order doesn't matter. So divide by 2 times 1. So that would be 12. And you can also look at that as 4C2 times 2C1. Now let's look at the case where the silver car is chosen first. Well, in this case, this still ends up giving you a scenario where 1 person gets a silver and 2 people get a white car. So this is actually not counted any differently than this one. Since the order in which these cars are given to people doesn't really matter, then we have already counted how many ways these cars could be given out because we used combinations to calculate how many ways we can select 2 white cars and 1 silver car. So this is 12 out of 6C3. 6C3 is 20. If I reduce that fraction, I can divide the top and the bottom by 4, and I get 3/5. That's the probability that 2 will be given a white car and 1 will be given a silver car. In number 3, the wording is a little bit confusing, so let's take out part of the wording and then simplify this. 200 randomly selected residents of apartments were surveyed. The results are organized in the two-way table below. Determine whether the number of residents is independent of the number of bedrooms. For example, is the event that an apartment has a single occupant independent of the event that an apartment has 1 bedroom? To find out if these events are independent, let's find the probability that an apartment has a single occupant. We can call that the probability of SO. The probability that an apartment has a single occupant, let's find out how many apartments have single occupants, 76. Out of how many people in total, 200. So that's a 38% probability if you plug that into a calculator. Now we saw earlier that if A and B are independent events, then the probability of A happening, given that B has happened, is the same as the probability of A happening, because it doesn't matter if B happens, they are independent. So let's check that with this scenario. We have found the probability that a unit has a single occupant. Now let's find the probability that a unit has a single occupant, given that it's a 1-bedroom apartment. Well, there are 90 one-bedroom apartments. So out of those 90, how many are single occupant? That would be 64. Now 64 out of 90 is approximately 0.71 or 71%. Well, here we see that these two probabilities are not exactly the same. They're not even close. So these two events must be dependent. If the probabilities were the same, these two events would be independent. And it should make sense that these events are not independent, that they are dependent, because how many bedrooms you rent out an apartment with should depend on how many people you're putting into that unit. If you are a single occupant, you are more likely to rent out a one-bedroom apartment. Number 4, 250 people are surveyed. Determine whether left-handedness is independent or dependent of playing a musical instrument. Let's first find the probability that someone is left-handed. The probability of being left-handed, there are 30 total left-handed people out of 250 in all. That's 3/25 or 12%. Now let's find the probability that someone is left-handed given that they play a musical instrument. I'll call that P. Well, if they play a musical instrument, there are 50 people who play musical instruments. Let's see how many are left-handed. 6 out of 50. 6 out of 50 is 12%. These events have the same probability, so these events are independent. Whether you are right-handed or left-handed has no effect on whether or not you play a musical instrument in this particular survey. Number 5, 297 people are surveyed, and the results are in this two-way table. Determine if a child knowing how to ride a bike is independent or dependent of them knowing how to swim. So let's find the probability that someone knows how to ride a bike. I'll call that B. The probability of knowing how to ride a bike, there are 225 people who know how to ride a bike, and there are 297 in all. In decimal form, that is 0.75 repeating, so that's 75.75 repeating percent, almost 76%. Now let's find the probability that someone knows how to ride a bike given that they know how to swim. Well, given that they know how to swim means we need to find out how many people know how to swim, and that is 200. Out of those who know how to swim, how many know how to ride a bike? That's 153. 153 divided by 200 is 0.765. That's 76.5%. These are very close to each other, so let's go ahead and say these are basically independent events.